I think one of the hardest concepts for linear algebra students is this notion of change of basis, but I want to break it down and show you it's not too bad. If we're talking about vectors, if we want to assign numbers to them, we have to have some coordinate system. For instance, here, if I talk about this pink point, I can see that it's going over some number of purple units, it looks like 3, and it's also going up some number of red units, it looks like 1.5. But if I take that same pink point and change the grid system, I'm going to get different numbers. Let's see. With this shading to help, it looks like I'm going about a half a unit in that blue direction, but actually 3 units in that green direction. So even though it's the same point, we would use different numbers to describe it. Now, if you've taken linear algebra and you've done something called change of basis, you've maybe seen formulas like this, but if you're like me, you always forget like where that inverse goes. Like maybe it goes there. And of course, the answer depends on what we mean by P. I'm going to break everything down. The setup is that we have some matrix and some coordinate system, and remember that describes some transformation. For instance, if we started with this red vector here, 1, 1, applying that matrix we'd get the vector 4, 6, which means that the red vector goes to the orange vector. What we would like is to have in a different coordinate system some matrix that describes the same operation. In other words, if we wrote down coordinates of the red and orange vectors in this coordinate system, which will totally be different, we still want some matrix that we can multiply those numbers by to get things to work out. In this coordinate system, that red vector actually has coordinates 0 and 1/2. So at the end, we're going to check and make sure our matrix is going to send us up to this orange vector here. The matrix A lives in a universe where everything is in the old coordinate system, and what we want is a matrix where everything is in the new coordinate system. For instance, in the new coordinate system, the vector 1, 1 actually refers to this point way over here because it's one blue vector and then one green vector. What will unlock everything is that since we want to start and end in the new coordinate system, we can use our matrix A in the middle, which is going to go from old to old, as long as we can convert from new to old and then back from old to new. Notice that these two matrices I've circled have to be inverses of each other, because, well, going from new to old is the inverse of going from old to new. This is good news because we only have to find one conversion matrix. The other will just be the inverse of it. Let's try to find a matrix that goes from the new coordinate system to the old one. In our new coordinate system, this vector here has coordinates 1, 0. But in the old coordinate system, what are we supposed to get? Well, I would say that's the point 3, 0. Doing something similar with this guy here, I can see that that vector in our old coordinate system should just be 2, 2. I know how to fill in the rest of my matrix. So P, which of course is just the matrix here, not these whole equations, is going to convert from the new system to the old system. Putting everything together, because we want to start with new and we want to end with new, and remember when we compose functions, we always start with some input on the right, we're going to go from new to old, that was our matrix P. We're going to go from old to old, that was our matrix A that actually does the transformation, and then we're going to undo what we did to get back to the new coordinate system. Here's all the matrices if you want to see all the details, but at the end of the day, when we calculate it, we got this matrix here for B. So I've put our matrix B in, and remember the coordinates of that red vector were 0, 1/2, and when I multiply through, what do I get? I get -2/3 in the blue direction and 3 in that green direction. Let's draw a picture and see what's going on. 2/3 of one of these blue vectors in the opposite direction gets me back there, and then I'm supposed to add 3 copies of the green vector. Let's see where that puts us. So I'm adding vector after vector, and right when I add the third one, you can see that everything is exactly as we promised. How exciting.